Welcome back to Large Scale Machine Learning. So we'll be continuing our discussion on large scale machine learning. And in this topic, we'll be talking about one particular algorithm to handle the case of data bound problems or memory bound problems, where we need to actually handle the data uh, by actually processing it in pieces rather than trying to load the entire data set into the memory at one go. So we'll be talking about scaling with instances using out-of-core learning. That means the entire dataset need not be loaded into the RAM simultaneously. Out-of-core or external memory learning is the technique used to learn from data that cannot fit in a computer's main memory or RAM. Here's a sketch of a system designed to achieve this goal. 1. A way to stream instances. So we actually read it in a continuous stream of bytes, but not the entire data set at the instant. Secondly, a way to extract features from the instances. So we stream in the data, and then we are going to not use every single bit of data. We are just going to focus on the features. So as the data streamed in, we extract the features from the instances or the rows of data. And thirdly, we need to have an incremental algorithm, an algorithm that can learn not all at one go, but at the different pieces or chunks of data as it's being streamed in. So the general idea for these techniques are what we call chunking. So the data is not loaded entirely into the algorithm all at one go, but we read in chunks of data, and from each of the chunks of data, we extract out the features that we want to learn from, and then we run an algorithm that can learn from chunks of data rather than having to have the entire data frame being available. So this is roughly how we actually achieve this out-of-core learning. So let's first of all, streaming instances. Basically, streaming instances may be some sort of reader that basically reads chunks of data rather than the entire file at a go. So one approach that emulates streaming data without the need of having an extensive infrastructure is to support chunking, to support um, is to chunk the reading of data. That means the data is being read chunk by chunk or groups of it rather than having the entire data being read in all at once. So for example, in pandas, there's actually the very common read CSV function. You can actually specify the chunk size. So if you specify a chunk size of 1024, it will read 1024 bytes at a time. If you specify a chunk size of 1 megabyte, you read 1 megabyte at a time. So the chunk size is the smaller pieces of information that's read in every time the function call is actually read. And so it means that basically you have to read it multiple times in order to read the entire data set. Right? But each time you read the data, you read only a small portion of it or a chunk of it. Now, streaming data is data that is continuously being generated from the different sources. So that's actually is actually more extreme than chunking. So chunking gives you in blocks, right? But streaming is actually a continuous flow of data from the different sources. So such data should be processed incrementally using stream processing techniques without having to access all of the data. The data could be stored in a streaming database. For example, so this is a handle streaming data. So we can store it into a database. For example, this one, the KSQLDB is an example of streaming database. So think about log information that's generated. For example, every time we access a particular website, the web log. That information is not, although it may be gigabytes is in size, uh, every time there is a new visit to the website, one line of in the log file is being generated. So this sort of data, if you actually feed it into machine learning algorithm and you want to actually learn what's the pattern of this visits to the website, that data is actually streaming data because the data is actually coming in incrementally, right? A bit by bit in a continuous streaming fashion rather than as the entire chunk at a go. Now we could store such streaming data in a file like what we do in the managed web servers, or we could have a specialized database that stores it with the timestamp. For example, this KSQLDB. Another one that does handling of this streaming data is what we call the Apache Kafka. This is an open source distributed streaming event streaming platform, and this is actually commonly used in a lot of companies. Next, extracting features. So extracting features could be any relevant way to extract features from the different feature extraction methods that are supported by scikit-learn. So we're going to try to extract the features from the data stream coming in chunk by chunk. However, when working with data that needs vectorization or where the set of features or values is not known in advance, one should take explicit care. A good example is a text classification problem where unknown terms are likely to be found during training. And it's possible to use a stateful vectorizer to make multiple passes over the data in order from the application point of view. Otherwise, one can turn up the difficulty by using a stateless feature extractor. So stateful feature extractor means that basically you are able to remember some of the results from the previous passes, whereas the stateless one basically is just a one pass thing, right? Whatever is being extracted, you only have one go at it. The problem is that not all the data may be available, especially if you talk about streaming data. Some of the more interesting data may be at the end, so it hasn't appeared yet. So your stateless feature extractor is not going to see it until later on. Whereas for the stateful one, we can remember from previous passes, so we can sort of append it gradually. Currently, the preferred method to do this is a method called the hashing trick, as implemented by the scikit feature extraction feature hasher. So we don't use the original data, but we create a hash. We use a hashing function to create a hash or a so-called compressed numerical information from the original data set. So the feature hasher for data sets using categorical variables represented as a list of Python dictionaries with the sklearn with sklearn feature extract.text hashing vectorizer for text documents. So this is the most natural language processing or text processing version of the feature hasher, which works with normal data. But if you have a lot of text, which basically means that you will be storing it into a list, then the text hash vectorizer works better for this type of documents. The idea is still to basically compress the information so that we can extract the key information and then pass it to the machine learning algorithm. So finally, we come to the last piece of the puzzle, which is incremental learning. So we talked about how we can read in the data in a streaming format or in chunks, so the data comes in gradually. Then we talked about how we can actually extract the features from these chunks of information. So the last piece of the puzzle is, what sort of learning algorithm can we use that learns from data in pieces rather than learn from the entire data frame at a go? And in fact, there are some learning algorithms that have these characteristics. So we're going to talk about this type of algorithm called incremental learning. So finally, for incremental learning, we have a number of options inside scikit-learn. Now, not all the algorithms can learn incrementally, but there's a substantial number of them. In other words, being able to learning incrementally means being able to learn without seeing all of the rows of data at once. All the estimators or scikit-learn algorithms that actually implement this particular function, the partial fit API function, are the ones that are able to actually learn incrementally. So you look out for, you can look in this part, the reference below, where we talk about different incremental learners that implement the partial fit function. Of course, you can also search for the partial fit function within the scikit-learn documentation. Actually, the ability to learn incrementally from a mini batch of instances, or sometimes called online learning, is a key out of learning as is the key to out of learning as it guarantees that at any given time, only a small number of instances are actually inside the main memory. So there are some algorithms like this, for example, the stochastic gradient descent. So this is actually a kind of algorithm that's used to train neural networks. So in a normal neural network, when we actually implement stochastic gradient descent, we actually take one example out of the entire data set as a sample of the training data for one epoch, right? So one epoch is the time taken to go through the entire data set. But if you want to calculate the gradient using the entire data set, and the data set is very large, let's say the 1 GB data set, right? It means that you actually have to do many computations in order to get an estimate of the gradient. So rather than doing that, the key to making it faster is to take a rough approximation of the gradient, rather than which we can do by taking a random sample. Just take one example out of all the millions of rows of data and use that as an estimate to calculate the gradient. Then we can adjust the weights and then run the one step of the iterations to try to reduce the error. So this is basically what stochastic gradient does, right? It essentially uses a random sampling method to estimate the gradient rather than use the entire data set to calculate the gradient. So it's actually a very efficient method, and gradient by default, this is an incremental learning method because your one sample out of your entire data set is actually just one row, right? So you only load one row out of the millions of data set. A way to actually enhance this is to randomly pick groups of data. So we load all these groups or batches of data first, and then we use them to run through many iterations of the stochastic gradient descent before we unload it from the memory, and then we load in another group batch of randomly sampled data from maybe further down in the chunks of data. So we do this incrementally or gradually. So gradient descent is one of the algorithms that implement the partial fit incremental learning, and stochastic gradient descent is a simple and yet very effective approach to actually implement many of these linear algorithms, right? Linear classifiers as well as regressors with loss function. So if you want to do classification, you can use the linear model SGD classifier. If you want to do regression, you can do the linear model.sgd regressor. And they can be used to solve it. And in fact, actually, stochastic gradient descent, by adjusting the loss function, you can actually implement a support vector machine-like algorithm as well as logistic regression. It's actually depends on the loss function that you use with the SGD, right? So the SGD loss function will determine whether it's logistic regression that you're doing or it's a support vector machine. So here are some advantages of the stochastic gradient descent or SGD. It is a really efficient algorithm and it's relatively easy to implement without lots of code to tune. And the disadvantage of the stochastic gradient descent include that SGD requires a number of hyperparameters such as the regularization parameter, how much regularization you want to implement, and also the number of iterations that you want to use. And of course, there's this thing called the learning rate that you can actually implement it, that can actually affect the performance of the convergence of the stochastic gradient algorithm as well. And the learning rate need not be a constant value. So you may want to adjust it so that as it approaches the minimum point, you want to actually reduce it so that it doesn't overshoot the minimum point. So you need to have that adaptive way of actually adjusting the learning rate. And lastly, it's sensitive to things like feature scaling. So the values that you are inputting in the features, the larger values tend to dominate over the smaller values or have a larger effect. So you need to do some sort of scaling so that the range of values are similar and you don't have any particular feature actually dominating over the smaller values. So strictly speaking, actually SGD is not a machine learning algorithm. It's actually an optimization method. So you can actually apply this optimization method to different machine learning algorithms. And in fact, SGD has been around for a long time, but it's only more recently that it has come to, people start paying attention to it because of its usefulness in handling this kind of partial fitting problem, right? Incremental machine learning. So in the past, other algorithms have taken the spotlight, but SGD is very helpful when we need to deal with large data sets where we are not able to load in and apply the entire algorithm to all the rows of data at once. So we can only apply to groups of data or small batches of data. So that's where SGD comes in very naturally to be able to handle these types of problems. So coming back to this, SGD is not actually a machine learning algorithm. So you can actually implement different machine learning algorithms depending on the loss function that you use. So for example, if you use the log loss function, then your SGD classifier basically works like a large scale logistic regression. So you have a very large data set and you want to apply it to the normal logistic regression, your scikit-learn will actually crash. But if you apply it to the SGD classifier and set the loss function to the log loss function, actually it will implement the logistic regression, but it does it in a partial or incremental learning manner. So the model is that when you set this, the model is actually equivalent to a normal logistic regression. Similarly, if you use SGD with the squared loss, then and a penalty of L2, this will be equivalent to a regressor with ridge regression, right? So it's the L2 loss with a MSE or mean squared loss. So it's similar to the ridge regression. And if you apply SGD classifier with the other loss, the hinge loss, it actually implements the other very popular classification algorithm, which is the support vector machines, linear support vector machines with the hinge loss. You can implement it in an incremental manner, in an incremental learning manner, using the SGD classifier. If you think about it, actually SGD classifier and SGD regressor, they correspond to a one layer neural network, right? You have all the input weights, and then we have apply some sort of loss function over these weights, and we can train it using gradient descent, using stochastic gradient descent. So it actually corresponds to a one layer neural network, so one single output neuron, and the loss that you define is basically the loss for that particular output neuron. So it's quite helpful and it's useful, and you can even do a multi-class classification by applying it to the one over the rest method, OVA method. So if you apply one over the rest, you don't only can do binary classification, you can do a multi-class classification as well. So very useful method, and as I said, it has really come into the limelight now, mainly because of this natural fit into problems where we need to actually do incremental learning. So here's an interesting exercise, and you should try this. It's at the Observable HQ, and it basically shows you the different effects of running different types of optimization algorithms over the same problem. So you have SGD, the stochastic gradient descent, then we can compare it with the more adaptive forms like ADAM, stochastic gradient descent with momentum, and then something called the RMS prop algorithm. Now, the center of the screen is basically a contour plot, which is basically trying to plot the loss function. So all the points with the similar loss value will have the same, they are actually on the same part of the circle, right? So each actually, you can see they're like concentric rings, like ring-like structures. This actually at the same color means that actually the loss value, the error value is the same. So the highest loss are the dark blue colors at the edge of the screen. And then in the center, there are basically two craters, right, where the loss value is minimum. So if your gradient descent algorithm is working correctly, then if you drop a ball somewhere here, right, at the top of the mountain, it will then start rolling down the slope, because the slope here, this is actually downslope because higher value of loss to lower and lower values until it reaches the minimum. And you can find that actually those algorithms that tend to overshoot, like the momentum here, because the momentum may be very large, went past and then circle around before coming back to lower value. Whereas SGD, you sort of goes down and then it approaches the lower and then reaches the minimum. And for the other more adaptive one, you can see that they actually reach the bottom a lot faster than SGD, right? Because they just go zoom in straight away, especially this RMS prop. So this, you can try dropping the ball at different locations, like in the middle, right? Does it go to the left or right? So there's a randomization, right? It could be either be left or right. But if you try to drop it at some unusual corner, like where it will where it will basically gather some velocity or speed as it rolls down, like maybe over here, you can see whether or not it will converge faster or lower depending on the algorithm. So it really shows that actually different optimization algorithms, they can perform better depending on the shape of the loss function. So it doesn't mean that one particular algorithm will always outperform the rest. But of course, The adaptive ones like Adam, they tend to always perform very well because they are adjusting the learning rate. So when it's very far away, the learning rate is very high, so it actually zooms down very quickly. But as it approaches the minimum point, it drops down the learning rate, so it doesn't try to um, there's a less tendency to overshoot the minimum value. But still, you can see that Adam, as compared with RMS prop, it did overshoot before coming back, but not as bad as the other one, right? The one with momentum. And in fact, in this case, actually, the SGD actually outperformed the Adam, right? Because it zoom in, whereas the Adam tends to overshoot a bit and then went past before coming back and actually approaching the minimum point. So try this out. This is a very interesting visualization, and you try two things. One is observe when you drop the starting point at different places, right? When in the middle here or at the different corners, and observe the trajectories for each of the different algorithms. Given that there are two low points here, and starting from the left side, basically you will try to the correct place would be to come here rather than to go over to the other side. But it is possible that you will accelerate very quickly, especially if you have a high momentum, right? You accelerate very quickly down here, then overshoot, and then if you are just at the right angle, right, you overshoot and then actually drop into the other crater rather than converge here. So that's the disadvantage of momentum, right? It looks at the previous value of change. So if you set it to too large a value, it tends to overshoot. But at least if this was not the minimum point, this was actually the best minimum point. At least with the momentum, it has a higher chance of actually finding the global minimum rather than getting stuck at the local minimum. So that's actually the trump card that momentum-based methods have. Okay, they have the ability to skip over local minima and try to explore a little bit further so that you can find the overall global minima. But the flip side of it is that there's a tendency to overshoot a little bit more than the other algorithms. And with that, we come to the last slide. So thank you for your attention.